what we did yesterday, we said, well, if we had this process to calculate the derivative. If we didn't know it had to have any meaning, we know that the derivative has a meaning. The derivative gives us the slope of the tangent line to the curve, which is representative of the rate of change of something, one variable with respect to other. So, for you physics people, velocity is the derivative of position with respect to time, and acceleration is the derivative of velocity with respect to time. So we can do this antiderivative thing just as a interesting fact, but it actually does have some usefulness, which we'll talk about in a second. Where does this? We'll actually derive the constant acceleration equations out in calculus form instead of in algebra form that we've done so far in calculus. In physics. Oh, by the way, I guess you probably noticed that I put your grades for physics. So I don't know. I'm going to wait till Tuesday to hand it out because it's kind of, I'll give you an idea of how it worked out. But like I said, they were within a few points of what I told you it was going to probably be. Some of you did a better job at doing the additional stuff than others, so that's why they're not exactly the same. Some did better and some did worse. Not worse than, everybody did better than initially, that was for sure. Okay, so we were saying the antiderivative is the function, and we'll call it capital F. So the antiderivative of small f is capital F. And it is the function whose derivative is the original other function that we're talking about. So the integral of f of x is capital F of x. The derivative of capital F of x is small f of x. And also, this antiderivative, we also use the word integral. And really, after this initial introduction, we'll just call it the integral. We call it the antiderivative now because you can see the connection between the derivative and what we're doing now. But integral will be the word that we'll tend to use, and I may accidentally say it just because that's what we normally say. So it's like Christian, I can't help saying Kendall every once in a while, and it really annoys him, but I can't, so. So what the antiderivative of small f of x being 3x squared is x cubed. And that's not using that formula. It's just saying what is the function whose derivative is equal to 3x squared? Well, the function is x cubed. So when I use the rules for derivatives, I get 3x squared. Okay? But there's actually more than one equation that has the derivative 3x squared. It could be x cubed plus 1, x cubed plus 2, x cubed plus any number, any constant. Because if we take the derivative of this, the derivative of any constant is 0, and so you still get the derivative here being 3x for all of these choices. So when we actually take the antiderivative or the integral, we always add this, what we call an arbitrary constant. So it says C is any constant number. We use the word arbitrary constant because arbitrary means that at this point it can be any constant. Arbitrary constant. So that's what C is. The question is, how do you find C? Well, we'll demonstrate that in a while. Don't write this stuff down. This is just kind of review on terminology that we used for derivatives. So remember, we use the prime designated that we're taking the derivative or finding the slope of the tangent line, and it's approximately equal to a small change in y for the function divided by a small change in x, or we can think about it as this differential dy divided by dx. And then we take the limit of that as delta x goes to 0 or dx goes to 0, and that gives us the exact value Another way we can think about it is f prime is the derivative of this y equals x function. So if y equals x squared, then we can show it as d, and I've got it in brackets. The d dx is kind of a way of saying I'm taking the derivative, and then in the brackets is what I'm taking the derivative of. So technically d dx of y is not exactly the same as the ratio of dy dx. So this represents the derivative, and this ratio of dy and dx represents just a small change in y divided by a small change in x, which approximates the slope if we use these as small changes instead of having a ddx of y. Okay. So they may look the same. We may see dy dx, but depending upon the context, it may be dy over dx, or it may be this form. We just leave the parenthesis out. Okay, what else have I got down here? So dy and dx are called differentials. We know that. And the delta y and delta x are like delta y and delta x, but they represent infinitesimal changes. So they're just to represent really small changes, but not equal to 0. So that's kind of a terminology thing. Okay, so now something new. When we do the antiderivative, to represent the antiderivative, we use this symbol right here. So just like the prime means that we take the derivative, the integral, we call this the integral sign. That tells us that we do the opposite of taking the derivative. We take the antiderivative. So if we want to find the antiderivative, but earlier when I asked this question in words, I said find the antiderivative, the function f of x squared. How do we represent doing that instead of using words? So what we do, so I'll say instead of saying take the antiderivative or integral. Okay, you can use those words interchangeably. To take the antiderivative integral of 3x squared, we can mathematically write the integral of 3x squared dx. So this integral sign tells us to take the antiderivative. This is the function we're taking the antiderivative of, and this little dx thing at the end is telling us that we're integrating with respect to x. If we integrated with respect to y, let's just to demonstrate something. If I had, whoops, what happened there? So if I did something like 3x squared dy, the integral of 3x squared dy would be 3x squared y plus c. Okay? So if I'm integrating this with respect to y, this part we just consider to be a constant. It's not a variable as far as the integration is concerned. Now this doesn't happen in our class. Okay, we always do it this way, but I'm just wanting to point out that if you did change this letter to something other than the one that's there, then this would be multivariable calculus, and then so when it comes to multivariable calculus, you might, this will be critical for us. We're not going to deal with that. We're just going to, it's always going to match. This variable here and the dx part is going to match that. So we can just get rid of that for right now. And so if I did that, the answer the answer to this would be x cubed plus c. Now, when we start talking about area, that the integral of some function is related to the area underneath the curve, you'll see why we use this dx. Right now, it seems kind of arbitrary. Why didn't I do some? Why did I use dx to indicate that I'm integrating with respect to x? I could use some other, made up something else. But there is some reason that's there. It has to do with the second part of integration, the second reason we do integration. So just for right now, just take that for granted that it's there to tell us which variable we integrate with respect to. Okay, so we just did this one. So if the second example, if we show the integral or the antiderivative of the cosine of x, that would be equal to the sine of x plus c. And that's because the derivative of the sine is the cosine. So the integral of the cosine is the sine. So we do the same thing if you take the integral of the sine of x dx. That ends up being negative the cosine of x plus c. And that's because the derivative of the cosine is negative the sine. So you have to have the negative. So when you take the derivative, the negatives cancel out to get to a positive result. So that's the mechanics of taking the antiderivative. Okay, we already talked about that. So differentiation is basically the opposite of integration. They're kind of like inverses of each other. Like the natural log and e to the x are inverses of each other, or the other inverse things. The sine is the inverse of the inverse cosine, and the inverse cosine is the inverse. Let me make sure I had max. The inverse of the sine is the inverse sine, or the arc sine. We'll talk more about that in chapter 5. Also, to show that mathematically, you can write out that the derivative with respect to x of the integral of f of x dx is the original function. So let's just demonstrate that. So if we start with f of x and we do the integration of it, so the first step here would be do the integral of x squared dx. That's equal to 3x, no, that's actually, this is equal to x cubed over 3 plus c. So that's the integral. The formula that we talked about the other day is you add 1 to the exponent and you divide by the new exponent. That's the power rule for integration. So then if I take the derivative with respect to x of what I just got, the derivative of the first one is going to be 3x squared divided by 3 plus 0, because the derivative of a constant is 0, and the 3's cancel out, and I get x squared, which is equal to f of x. So that's kind of demonstrating that, if you take the derivative of the integral or the integral of the derivative, you end up with where you started. It's like if you take the natural log of e to the x, that's equal to x, and if you take e to the natural log of x, that's x. So it's, that's the property of inverse functions. F of g of x equals x and g of f of x equals x. It's not, we're not talking about composite functions here, but we are talking about doing one and then doing the other, and you end up back to where you started. Okay. We mentioned this yesterday, or the day before yesterday. So remember the differentiation rule for product for a power, the derivative of x to the n is n times x to the n minus 1. We know you know that because we had that one problem that just did that on the test. So the integral rule is that the integral of x to the n dx is equal to x to the n plus 1 divided by n plus 1 plus c, and n cannot equal negative 1. Up here, n could not equal 0. So they work for every value of exponent except here's for 0 because x to the 0 is, what is x to the 0? It's a constant. So that wouldn't give you the right answer for the derivative of a constant, I don't think, which is 0. And then the same case here. So the only function that we can't, only exponential function that we can't, not exponential, but power that we can't handle this would be what is the integral of 1 over x dx. That's when n equals -1. It'll turn out in chapter 5 that this is equal to the natural log of the. So for that one special case, it turns out it's the natural log. But otherwise, for any other power n, all you do is you add 1 to the exponent and you divide by the new exponent. So let me just demonstrate that on something that, we've already done it, but say x to the 2.1 power. If I want to do the integral of x to the 2.1 power, it's going to be x to the 3.1 power divided by 3.1 plus c. So I picked something that wasn't an integer just to show you that it can be a rational number, an irrational number, it can be a negative number, it can be any number. And these are all the rules that are in your book, and you're not going to have to memorize that because from now on you'll get a sheet of paper with your tests that basically is going to have all these rules. So we're just going to skip over that for right now. We've already mentioned most of them anyway. And we've already done something like that. So we're going to move on to this one. So it's how do you handle the formula when you have a expression like 1 over x squared? Well, you do the same thing that you did when you took derivatives. This formula only works when you have x to some power n, not 1 over x to some power. So we have to rewrite the original function as a negative exponent and then apply the rule. So just like if we were going to take the derivative of this, we would rewrite it as x to the minus 2 power dx. In that case, n is equal to -2, so n plus 1 is going to be equal to -1. So when you do the integral, you would get x to the minus 1 power, pardon me, shouldn't put that integral sign there. So when you take the integral or the antiderivative, the formula says that the answer is x to the n plus 1 divided by n plus 1 plus c. So put a little equal sign there. So we rewrite it, use the formula, then you take the term with a negative exponent, move that to the denominator. And then if it's to the first power, you just drop it. So you get -1 over x plus c. So why don't you guys try that one? See what you get. There's the formula up here. N is not equal to 1. Actually, that should be -1. So there's your answer. So we rewrite 3 over x to the fourth as 3 times x to the minus fourth, and then you apply the formula. So you add 1 to negative 4, which is negative 3. So you have x to the negative 3 divided by negative 3. The 3's cancel out. So you get negative x to the minus 3, and we rewrite that as negative 1 over x cubed. You can do the same thing with radicals. So you would rewrite this as 3 times x to the 1/2 power dx. And then you're going to use the formula. So in this case, n equals 1/2. So what you're looking for is n plus 1. That's going to equal something. So again, you guys can do the rest of the problem. So there's your answer. So you get 2x to the 3/2 plus c. So 1/2 plus 1 is 3/2. So the integral is x to the 3/2 divided by 3/2, which is, you take the reciprocal of this. So instead of dividing by 3/2, you'd multiply by 2/3. Cancel the 3's out. You're left with 2. And, you could write this as 2 times the square root of x cubed, I guess, plus c. This is fine. The only time I want you to rewrite it in kind of cube root or square root is if it's to the 3rd power or the 1/2 power. If it's to the 2/3 power, to the 3/2 power, you can just leave it as a fractional exponent. Okay, I'm going to skip over that. So the question is, how do you figure out what C is? Well, C is determined by specifying some initial conditions. So you would say at x equals 3, y equals something. And though specifying both x and y at some condition, some value, you can find C. Now I'm going to demonstrate this actually. Well, let's see. I want to make sure I have time to. Yeah. So if I do the integral of, say, x dx, the exponent is 1. So I add 1 to the exponent. I divide by the new exponent. And I have this arbitrary constant c. So what these curves represent are all the possible, well, not all the possible solutions, 4 of the possible solutions. Each one of these has a different value of c. And all you have to do to figure out which one of these curves you're on is to specify some point in space, because none of these curves overlap. They're all offset vertically because we're adding a c. Remember, if you translate something vertically, you add a constant. If you want to take it down, you subtract. If you want to move it up. So these are all separated by, in this case, I guess 2 units. In this case, yeah, 2 units. So all you have to do is specify anything. I could specify y equals 0, x equals -2 to fit on this curve, or I could specify this point. A lot of times we do it at x equals 0. So let me just, so the way I would answer this question, I would say, what is the solution to the integral of x squared dx if when x equals 1, y equals 4. So this is what we call this the initial condition, or just a, yeah, even though it's not at x equals 0, we still call it initial condition. So what you would do is you would do the integral. So we'd add 1 to the exponent, divide by the new exponent, add our arbitrary constant c, and this would be equal to y. Okay, so this is the solution, and this is the equation. We get y equals x cubed over 3 plus c. So then all you have to do is plug in your initial condition and figure out what c is. So for y I put in 4, for x I put in 1, and if I solve for c I'll get 11/3, because this is 12/3, and I subtract 1/3, I get 11/3. So if I don't specify the initial condition, then I have this result where I don't know what c is. But if I specify any pair of x and y, I can figure out what the value of c is, and that would put me on a specific curve over here. Or maybe not one of these specific curves, but it would tell you exactly which curve you're fitting on. So I want to do the physics part here, so I'm going to skip over this. So we can do the so what for physics, we know that the derivative of the velocity with respect to time is equal to the acceleration. That's just the definition of acceleration. If we have constant acceleration, let's say we have constant acceleration of -9.8 meters. Well, we'll just say it's a. So we have a constant acceleration of a. So a is a constant, not a variable. So what we would do is we would multiply both sides by dt. So I'm converting this derivative into the differential form. So instead of saying it's d dt of v, it's dv over dt. Now, if I integrate both sides of this expression, just like any math thing, if you do the same thing on both sides. So if I integrate dv and I integrate a dt, well, the integral of dv is kind of like, if we go back here, keep going back here, there. You know, if you take the derivative of the integral, you get the function. If you take the integral of the derivative, you get the function. So it turns out that if you integrate dv, you just get v. So the velocity is a function of time. The integral of a dt, well, a is a constant, and the integral of dt is just t. So remember the derivative with respect to x is equal to 1. So that means the integral of 1 dx is equal to x. So that's what I'm doing here. The a, because it's a constant, I can pull outside the integral sign. And then the integral, what I have left is 1 dt. The integral of 1 dt is t. And I add this arbitrary constant c to the equation. So that kind of looks like one of the equations we've been doing in physics, right? The equation we've been using in physics is that v is equal to v0 plus at. So that's this term, and that's that term. So what is it? Where does this come from? Well, what you do is you say at t equals 0 that the velocity as a function of time is equal to the initial velocity. So I'm specifying my initial, these are initial conditions. So I'm saying it, when I start the process, we have some specified initial velocity. So what to do that, you take this equation, v of t again, let me rewrite it. So you got v of t is a constant acceleration times time plus c. So for t I put in 0. So a times 0 plus c, and for v of t, I put in v0. So what I'm doing here is doing v of 0 time, which is v0. So turns out the arbitrary constant is equal to v0. So I can stick that back in now into my, we call this the general solution. That's when you have an arbitrary constant. So we put in our specific velocity that we're specifying, and we get the velocity as a function of time is equal to a times t plus the initial velocity, or v is equal to v0 plus at. So that is one that we've used all the time. So that's the calculus way of doing it. You start with a constant acceleration. You say that the velocity or the acceleration is the derivative of velocity with respect to time. Up there, you put it in differential form. The integral of a derivative or differential is the function, and the integral of just dt is t. This, because this is constant, it just moves along just like constants move along in derivatives. We end up with this arbitrary constant c, but we specify the initial conditions, and that allows us to figure out what c is. And the initial condition is that the initial velocity is v0 or specified. Okay, so that's the first equation. Now the second thing we do is we say that, if you remember from physics, that the derivative of the displacement with respect to time is equal to the velocity. So again, we can take this and put it in differential form. So dx is equal to v times dt. So it's just like we did with the acceleration thing. Now, acceleration here was constant. The velocity I just calculated from the previous step. So what I'm going to do is I'm going to substitute in for v, I'm going to put in v0 plus at dt. So to find the actual displacement as a function of time, I'm going to take the integral of dx, and the answer is the result will be x as a function of time. Just like over here, when I took the integral of dv, I got v as a function of time. Now, what I have here, I have two integrals. I have v0 dt, and I have the integral of at dt. So one of the rules of integrals is the integral of a sum is the sum of the integrals. Well, here it's just like before. v0 is a constant. That's my initial velocity. The integral of dt is t. So just like before, when I integrated a dt, it was just a times t. So over here, the integral of v0 dt is just v0 times t. In the second integral, I have my constant a, and then I have the integral of t dt. Well, this is a polynomial with an exponent of 1. So when I integrate it, I add 1 to my exponent, and I divide by the new exponent. And then I add my arbitrary constant c again, which is, it's a different arbitrary constant than I used before, but we tend to use it all the time, no matter what. So again, a constant, we say you can pull that outside of the integral sign. Then we have the integral of t to the first power dt, add 1 to the exponent, you get 2, divided by the new exponent, which is 2. So that looks pretty familiar too, doesn't it? v0t plus 1/2 at squared. The way you handle the arbitrary constant c is we have another initial condition. We have two initial conditions in this case, one for velocity and one for displacement. So the initial condition for displacement, which is x, actually for position, x is really position, not displacement. So for position is that the value of the displacement at x equals 0 is 0. Okay. So we're saying the initial displacement, the initial position is 0. We always define that as 0 arbitrarily anyway. So if we apply this initial condition to this equation, we'll get x of 0, which is 0, is equal to v0 times t equals 0 plus a times 0 squared divided by 2 plus c. Well, actually, we don't have to let it be 0. Let's just we'll put it as x0. It has some initial position, x0. So it doesn't have to be 0. Most of the time it is 0, but it doesn't have to be 0. So we're going to call that x0, just like we said this was the initial velocity. This is the initial position. So when we stick in t equals 0, these two terms go to 0, and you get the arbitrary constant is the initial position. So our final equation, x as a function of time, is going to be equal to the initial position. I'm going to move this to the front. So it's going to be c, which is x0, plus v0t plus 1/2 at squared. And if we say that delta x is the final position minus the initial position, we can then write this as delta x is equal to v0t plus 1/2 at squared. So that's equation number 3 in physics. And we did it a different way when we did it algebraically. But calculus-wise, we ended up taking the integral of the velocity as a function of time. Where is it here? This one, which we'd gotten from the previous step. And then we just used the rules of integration. The integration of a constant is just that constant times the variable. That was where we got, wherever it is, it's probably up there somewhere. And the integral of this polynomial t to the first dt is t squared over 2. And we end up with our very familiar thing. So, if you take calculus-based physics, the only difference is that you may be given an acceleration which is not constant. So instead of dv dt being just a, it may be some function of t. And therefore you have to do a slightly more complicated integral. But that's pretty much it as far as, calculus-based physics versus algebra-based physics. One is the derivation of the equations that we use. And secondly is if you have the equations that we use for constant acceleration. And also if you have an acceleration that's not constant, you can deal with that. If you have it as a function of time, then, and that's, where would you get acceleration as a function of time? Well, if you had force acting on something as a function of time. So you'd get, what you would basically, from a calculus standpoint, is you would, if you had a calculus physics problem, you might be given, be given the force as a function of time. And then the second law, Newton's second law, would say the acceleration as a function of time is equal to the force, I'll use capital F, force as a function of time divided by the mass. And then once you had that, you could say, well, the velocity as a function of time is the integral of the acceleration as a function of time. And so you'd have to do, like I said, a little more complicated integration, but it's not super hard. They usually are polynomials. You could do that. Okay. So what is today? Today is Thursday. By next Thursday, yeah, we'll go ahead and assign those today. We'll go back and do maybe 2 small problems. We'll do this as another example of how you can use the antiderivative to come up with a solution. And that's, the 2 basic ways that you use integration is you solve what we call differential equations. And that's what we did kind of in a simple case with relating velocity to acceleration. We had a differential equation, which meant that our equation didn't say y equals a function of x. It said velocity is a function of the derivative, or the acceleration is a function of the derivative of the velocity. Actually, the way around. But a lot of times in physics, the initial equations you start with say the derivative of something equals some mathematical relationship. And what you want to do is you want to find out what the actual function is, not the derivative. So as far as the acceleration, we knew that the acceleration was constant. That was specified. We wanted to know what the velocity was. So we had to integrate the acceleration to find out the velocity. This next example that we'll do tomorrow is looking at population growth in bacteria. So if you're a biologist, a biology major, and you want to know how fast some infection is going to grow, then you could use calculus because you know what the rate of change is going to be as a function of time. You want to know what the population is, so you could use calculus to get that. The second way of using integration is to find the area underneath curves, and we've done that in physics. When we had that, when we were trying to figure out how the velocity of that cart changed, we measured the force as a function of time, and we numerically found the area underneath the curve, and we said that was equal to the change in momentum. So there are other things besides that in examples in physics where the area under the curve represents some physical quantity. It's not just some arbitrary area underneath the curve. It actually means something. And that's what we'll do in section 2. We'll start on section 2 probably halfway in class tomorrow. So that's it for today. Remember, you have physics test tomorrow.